I'm Ryan. I'm a science teacher.
I'm Cheryl, and I slept through science.
Each episode will tackle a science question you may have learned in school, but can't quite remember or fully explain.
And I'll take the risk of asking the dumb questions so that we can all understand the science we slept through.
The bell has rung. Let's get started. Welcome to Lesson 2.
Yay! So, Ryan, I was thinking about moments in science class that I remember from my childhood/teenage years. And I think my most memorable science teacher was a teacher I had in 8th grade. And he was from England. And so, I think it was, he just had a good personality. He went on a Japan trip that I was a part of. So I just got to know him better in general. But also hearing science taught with a British accent is very good.
Oh, it makes everything better.
Oh, for sure. So first of all, please start speaking in a British accent.
Okay.
Maybe don't.
Yeah, probably not.
But also, there's one quote I always think about when I think about this teacher, because he was very passionately explaining a concept to us. And he said, if you divide the sugar cube in half, it dissolves faster.
Okay.
So that's just thinking about a fun quote from a moment when I was paying attention in science class. And I still remember, if you divide that sugar cube in half, it will dissolve faster. So there you go.
That is great. Can I ask you a question about that, Cheryl?
Sure.
Do you know why?
Because there's more surface area, probably.
More surface area where?
On the sugar cube.
Okay, more than?
When it's whole.
Okay, so why would that make a difference?
Because it dissolves from the outside. It's whatever's touching the water that's dissolving. The stuff on the inside that is not touching the water is not yet dissolving.
Okay, and what does it mean for something to dissolve?
Okay, so this is one of those things. I know dissolving is a thing.
That is correct.
I cook and I bake and I know how to make simple syrup because you boil water and sugar, and then it used to be water and sugar and now it's simple syrup. So what I don't know is, does the chemical compound, I don't even know if that's the right word, chemical compound, it's a thing I've heard. Does that actually change? Or I know, I could say this. I could say the sugar breaks down somehow in the water to where there's no longer granules of sugar, but it's just a part of the liquid now. Has it become liquid? Has sugar, because that's different than if I make caramel. So when I make caramel, I just have sugar in a pot and I turn the pot on and stir it constantly until it's liquefied. So that is sugar taking a liquid form. But I think there's something different than sugar taking a liquid form because water is involved. And also you can do it at room temperature. And so it's not I know everything. Okay, I know everything has gas and then solid and then liquid. Not in that order. In that order, I don't remember the order, but I know that those are the 3 states of matter, if that's a term. So the state of matter of the sugar when I boil it has become liquid. But if I put room temperature water and I put sugar in it, it's not quite the same thing that's happening yet. It still becomes a part of the liquid somehow. Or has it just become so microscopic that I can't feel the texture of it anymore? Or does it actually change? Does the composition of it actually change? And then I also know if I were to take boiling water and pour it on sugar, that whole process would happen much faster. I know this to be true.
Wait, faster than what?
Room temperature water.
Oh, okay. Okay.
I know that's true. I don't know why. It's hot. So something about it, I know that's true. You take that's just that will speed it up. And then if it was like an ice cube and sugar, it would just never really, well, I don't know. I mean, if the ice cube started to melt, like eventually something would happen. But if you just took a sugar cube and put it on an ice cube in the freezer, like they would still just both be there. They might stick together eventually, but they wouldn't actually like become one. So I know temperature is an aspect of it as well. These are the things I know and don't know.
That's a lot. That's a lot, Cheryl.
There's a lot I don't know. So
But there's also a lot that you do know.
Yes, I know how to make caramel. I made this delicious caramel apple spice cake, and I melted sugar, which was horrifying to just put just sugar in a pot and melt it. But
yeah,
it worked.
Yeah. Wow. Okay. So there's a lot there.
Mm-hmm.
Let me see kind of where to start. So I think, first of all, a lot of your thinking is on the right path, I guess.
Okay.
So, and you're asking a lot of questions that are the right questions too.
Okay.
Like one of the big questions you asked about was like, what's actually happening to the sugar?
Yeah.
Right?
Yeah.
And like if I were to press you and say, what's happening to the sugar when it's dissolving, and you had to say something, what would you say?
I would say that it's actually like chemically like actually changing. There's actually a change that happens, and somehow the water molecules and the sugar, is it also molecules, like become a new thing.
So then my follow-up question on that is, once it's dissolved, is it still sugar? Do you think?
Well, it's sugar water.
Okay.
But I don't know if that still like is under the umbrella of sugar or not.
Okay.
Like when I make simple syrup, that's also sugar water. It happens a lot faster because it's heated. But yeah, because if it dried, it would be sugar, right?
There you go. Yes.
Yeah. Okay. So it's still sugar.
As a matter of fact, have you ever made rock candy before?
No, but that's a thing, right? Is it like heat it and then you dry it?
So basically what you do, it's super easy and anybody can do it. I've done it a bunch of times. It's super easy. You could do it with your stepson. It would be a fun thing to do. You just dissolve a bunch of sugar in really hot water.
Okay.
And then you usually pour it into a cup. And
the strings.
Yeah,
I think I did
put
it
like
in
a
school
pencil
one time.
and you like tie a string around it and hang it down in the water, usually with something to kind of weigh it down. And then you have to leave it somewhere to let the water evaporate, like in a windowsill or something like that. And then over several days, the water will evaporate and the sugar will recrystallize on the string and you make rock candy.
Okay, now I want to do that. That sounds so fun.
It is fun.
That sounds awesome.
But why on earth does it work? Okay, so many things. And I'm going to try to give it to you in a way that makes sense and that we can build upon. Okay. So the first thing I think I'm going to start with is what happens to the sugar and is it still sugar? Because I think that's kind of what we were just talking about. It is still sugar because you said you can get it back again. Right?
Yeah. Yeah.
And so that is this idea that you've probably heard of, whether there's a physical change or a chemical change to a substance. So you can change something physically, but it's still made of the same chemical. And I'm using chemical in the science sense, which
not like ew, there are chemicals in this food. Like not that sense.
Not that sentence.
Okay.
The sentence, hey, all of food is made of chemicals. Water is a chemical. Oxygen is a chemical. Yeah. So
we need to talk about that someday.
Write it down. So a chemical change is where you actually change something from one substance to a different substance, and it's not the same anymore.
Can you give me an example?
Baking a cake. Because you heat it up, and the substances actually, the actual things that make it up are different at the end than at the beginning, and you can't undo it and get the original stuff back.
Is that a good rule of thumb that maybe doesn't 100% apply, but mainly applies is that you can't undo it?
Yep. And again, there are exceptions to that.
Sure.
But yes, that's a general rule, is that if it's a chemical change, you can't undo it. And if it's a physical change, you can. The most common type of physical change is one you already mentioned. It's called a phase change.
Okay.
You mentioned the 3 states of matter or phases of matter: solid, liquid, gas.
Mm-hmm.
There's actually 2 other ones, plasma and Bose-Einstein condensate, but you don't need to know those.
Is that like when they say there's more colors in the rainbow because there's ultraviolet or whatever it is?
No, it's a little bit different than that.
It seems the same, because it's like we all learned about these 6 rainbow colors, and then all of a sudden they're like,
okay, you need to write
just
down
kidding.
colors of the rainbow and how many are there, because we need to come back to that, because that's a good question.
Okay.
And I love talking about color and light because it's amazing. So write that down.
Okay.
But not right now. So the easiest physical change is from solid to liquid, liquid to gas, or the reverse, or you can technically cheat and skip a phase. You can go from solid straight to a gas. And if you've ever played with dry ice, that's what dry ice does. Because it goes from a solid to a gas. It doesn't turn to a liquid first. It cheats.
Okay, well, now I'm going to have to write down, how does dry ice work?
Yep, you can do that too. We're just getting all sorts of questions. So the sugar dissolving, or technically anything dissolving, if it's truly dissolving, is a physical change. It is not actually changing the chemical structure of whatever the thing is. And you can reverse it and get it back. Now, sometimes it's tricky to do, but you can actually do that.
Okay, yeah.
Okay. And like we said, you can evaporate it out. Similarly, when you talked about, you can also melt. Melting is one of those physical changes. Okay. And so when you're just melting something, that is going from a solid to a liquid. To help explain what I mean, because now we're going to go into things that you can't really picture, I actually have some physical models to show you, Cheryl.
Do you have visuals?
I have visuals.
Yay!
And since when we're recording this, I'm still teaching from home. And so I actually already had these things at home. So it actually works pretty well.
Aw, congratulations.
But, I'm going to show you, and I'm going to hold this up.
It looks like balloons.
They do look kind of like balloons. So this is a model of a particular molecule called glucose. You may have heard of glucose before. Exactly. It's one of the forms of sugar. There are actually several forms, but this is the simplest, one of the simplest ones. Okay. And so all of the little black circles or balloons are carbon atoms.
Okay.
All of the red ones are oxygen atoms, and all of the white ones are hydrogen atoms.
Okay. And is this the correct number of each of those for one glucose molecule?
Yep.
Okay. And there's equal parts of the 3 colors?
There are not. So the formula, the chemical formula for sugar, for glucose, is C6. So there should be 6 carbons, the black ones.
Okay.
H12.
The white
12
ones.
of the white hydrogens.
And they're attached to the red and the black.
Yep, it depends. Yep, because there's right now there's twice as many hydrogens as there are carbons, right? And then O6.
Okay. So there's 6 red ones.
Yep. So there's not the same number of everything. And actually that's pretty common. Hydrogens kind of go everywhere because you can see they're a little bit smaller.
Mm-hmm.
And they easily kind of just attach pretty much anywhere.
Do they care where they attach?
They do. But that's a great question for another time. So this is a glucose molecule. If you change this molecule and break, so what we call them bonds. Okay, the different atoms are connected to each other. And if you pull them apart.
I didn't know they pulled apart.
Yep. So if you pull them apart, you can actually change what this chemical composition is. If I added more carbons and more oxygens and hydrogens, it wouldn't be glucose anymore. It would be something else. Cool. And that would be a chemical change.
But when I dissolve the sugar in water...
When you dissolve the sugar in water, what you have, and unfortunately, I don't have enough of these to show you, but pretend I had a whole bunch of these next to each other.
Okay.
Right? That's what a sugar cube is a whole bunch of individual glucose molecules, sugar molecules. Technically, I think it's sucrose, but we'll just say glucose, that are all packed together.
Yeah, but how many like in a grain?
Yes, that's correct. I have no idea how many molecules are in
But
a
okay,
grain.
is it like 1? Is it 100? Is it
Oh,
like
no.
what's
It's
an
like
estimate?
it's like I would say millions or trillions.
Okay. That's I
I mean,
just wanted like a
probably not trillions, but
ballpark.
like like
Okay.
millions probably.
Okay. So like
Yeah, a
1 grain of
lot
sugar,
is
not 1 sugar cube, but 1 grain
right is
has
still
a
going to have
ton of those.
lots of these. Yep.
Okay.
Lots and
Okay.
lots and lots. But we can't tell because there's so many and they're packed together and they're sort of like connected next to each other.
Mhm.
When you put it in water, here's a water molecule, also known as
H2O.
exactly
And there's
H2O.
2 H's and 1 O.
Exactly, right?
Mhm.
Sometimes it's also, you'll like this, referred to as the Mickey Mouse molecule. As you can see why.
Not listeners, but viewers can find a hidden Mickey in this episode.
Yes. And we will try, by the way, if you're listening and have no idea what I'm showing you right now, we're going to be taking some screenshots from this and putting them up on our social media so that you can kind of get an idea what visuals we're talking about. But the water molecules get in between the different sugar molecules.
Why?
Because water is attracted to different parts, especially like you see how you've got this part here that has the red oxygen and the white hydrogen.
Mm-hmm.
And there's a lot of them kind of on the outside of the molecule.
Yeah.
They look real similar to water, don't they?
Yes.
They're just missing one part. So actually the hydrogen right here that's on the end gets attracted to part of the oxygen here. Not enough to bond it, so it doesn't pull apart.
So it's not a chemical change because it's not bonding with this.
Exactly.
Okay.
But it's enough to kind of get in the way and to keep it from staying connected to its other sugar molecules. So a whole bunch of, and this is where, again, I don't have enough hands, but a whole bunch of water starts going around the glucose molecule, the sugar molecule, and keeps it from being connected in a large piece where you can see it. And so dissolving is when now you've got, I'm going to say for our purposes, a single sugar molecule surrounded by a whole bunch of water molecules. And each of those sugar molecules gets separated from the rest of them.
So that's why texture-wise and visually, you don't see the sugar anymore because it'd be hard to see. Honestly, it'd be hard to see even 1 grain of sugar in a glass of water.
Yep.
And so once that 1 grain separates into individual molecules, you're just not going to see that. You're not going to feel it.
Right. And there's way more water molecules in there than there are sugar. So you can even see like 1 water molecule is way, way smaller than 1 sugar molecule. Right. So they can.
So even if you did equal parts sugar and water, there are still more water molecules in a half a cup of water than there are sugar molecules in a half a cup of sugar.
Correct. Now, you wouldn't probably be able to dissolve a half cup of sugar in a half cup of water, I don't think.
I mean, when you make simple syrup, you do equal parts.
Oh, do you do 1 and 1?
Mm-hmm. Yeah.
And you're heating it, though.
You're heating it. Can we talk about heat?
So there's the other piece. Yes.
I want to talk about heat.
Yes. So, but before we do, is this sort of making sense what's happening?
Yeah.
And that's what it means to dissolve. But
they're
that's
pushy.
why.
That's all they are. They're pushy.
They're pushy. And that's why if you drink sugar water, you still taste sugar. Because there are still sugar molecules in it. They're just separated from each other. And that's why when you evaporate the water away, right? So there's less water to go around the sugar molecules so they can start sticking together again and you can make rock candy.
Okay. Mm-hmm.
But now what does the temperature have to do with it?
Yes.
Because you said, what did you say about temperature?
I said that if you poured like boiling water on sugar, that would happen so quickly. Mm-hmm. And if you had freezing water, it would happen way slower or maybe not at all.
Yep. Okay. So now I'm sharing my screen with you.
Okay.
So that I can show you this simulation. And this is a great simulation. And we can link to it a little bit later. So this is going back to what you said, what we talked about with phases of matter.
Okay.
Okay. So think of each of those dots, each of those little circles as a whole molecule now. Okay. So since we're talking about sugar, you can leave it as one sugar molecule.
Okay.
Okay. So this is a solid. Okay. The molecules are there. They're moving around, but they're basically staying more or less in the same place in relation to each other.
Oh boy. At some point we're going to talk about the fact that molecules are moving.
Yep. We can do that too.
Okay.
As you add heat to molecules, they move faster. So see how they start to move faster? And now they're starting to kind of come apart a little bit. Do you see that?
Yeah.
That's melting. It's melting. And even a few of them have broken all the way through because they have enough energy that they are moving like up there. And that's a gas. So this is like liquid down here because they're bouncing around and doing some of these. This isn't the best example, but it still works. And if I heat it up enough, I can give enough of the molecules enough energy that they will turn into a gas.
That feels a lot like boiling water, how there's steam.
Yep.
That comes up.
Although technically the steam itself is, you've been lied to, the steam is actually liquid water. It's not actually water vapor, but that's neither here nor there. You could write that down as another question.
Oh my gosh.
Okay. So that's solid, liquid, gas.
Okay. Energy.
Yeah. So
heat produces energy.
Heat is a form of energy. Yeah. And so if you heat something, what you're doing is you're causing its molecules to move faster.
Okay.
Okay. The same thing is true with the water. So let's go back to our example. If we have glucose molecules, sugar molecules, and a whole bunch of them are connected to each other, and you've got water that's trying to get in between them.
Okay.
If the water is moving around slowly, it's not going to get between them quite as quickly. But if it's moving around faster because it's hotter, it's going to be able, first of all, it's got more, it's just got more oomph in its motion. So it can kind of like push its way in easier. And it's moving faster. So it's going to work its way in faster. So it's going to actually get in between those sugar molecules more quickly, therefore dissolving the sugar more quickly.
Yeah. Cool. That makes sense.
Yep.
Yeah.
So then to bring it all the way back to the original question, if you cut a sugar cube in half, it will dissolve faster. Right? And you said you thought that the reason was because of surface area.
Yes.
And that's correct.
Okay.
But this is what's going on at the surface at a atomic molecular level, right? Is because if you have more surface area, you've got more of these sugar molecules that are already physically separated from each other. So there are more places for the water to start to work its way in to separate those molecules from each other.
Yeah. That makes sense. Cool.
That's dissolving.
That's dissolving.
That's dissolving.
Yay.
Okay, so there's one other thing that I will mention, and I think it will frustrate you, and you'll write it down as another question as well.
Okay.
Because you talked about the ice cube.
Yes.
And you said if you were to put it on the ice cube, then it wouldn't actually dissolve.
Or not very much.
Or not very much. And that's mostly true. However, if you put the sugar, let's say you sprinkle some sugar onto the surface of an ice cube, you can actually get the ice cube to melt faster than if it's just standing there on its own. But that's another topic.
Whoa. Is that like how they say that if you put salt in water, it'll boil faster?
Yes. However, while that's technically true, when I was in college, we actually calculated how much faster it would make the water boil, and it's not enough that you would ever notice. You'd have to add so much salt that it would be disgusting to eat anything that you made in it. So you add salt to add flavor to your food, not to make it boil faster.
Okay.
But yes, that's what people claim.
It's true. It's just not enough of a difference that anyone cares.
Right.
Okay.
Yep. Okay, Cheryl, it's time for your pop quiz.
Ooh.
It's your favorite part.
Nope.
Oh, okay. Question number 1. Is sugar still sugar when it dissolves? How do you know?
It is still sugar because the molecule composition has not changed.
Excellent. What would be a practical thing, since you can't see the molecules, that could also give you a hint that it is still sugar?
If I believed I could reverse it and make it sugar again.
Okay, if you believed it. Just got to believe it hard enough.
Just believe in yourself and follow your heart.
Follow your heart.
Mm-hmm.
Yeah. Mm-hmm.
It's good with science a lot.
It really is. Yeah. All right, question 2. Describe what dissolving looks like on the molecular scale.
Whatever the... Well, it's got to be liquid. Oh, we didn't talk about that. Dissolving has to happen with a liquid and a solid.
It has to happen with a liquid. I think you can technically...
It could be 2 liquids?
It could be 2 liquids, yeah.
Okay, like honey and water.
And actually, technically, I think you can dissolve a gas in a liquid as well.
Okay, cool. But there has to be a liquid.
As far as I know, yes, there has to be a liquid.
Okay, so the molecules in the liquid get between the molecules in the other substance that are buddies.
Yep.
Neighbors. They like just barge in. They're super pushy. They just like get right in there. So that on a visual level, you can no longer even see that one substance. Yep.
Great. Question 3. Why does increased surface area lead to faster dissolving?
There are more places where that liquid can start that process of getting between those molecules because there's more surface area. So more of the molecules are exposed.
Exposed? Oh, this is a clean podcast. All right. Question 4. Why does hot water dissolve things faster than cold water?
Because heat equals energy. And energy means that the molecules are moving more.
Mm-hmm.
And if they're moving more, they are either coming at those other molecules with more force, or they're even more pushy. It's like a mosh pit.
Sure.
And so they get between those other molecules much faster because of the movement. It just makes that whole process happen faster.
Great. Yeah, but I would say you have a good understanding.
Yay! Gold stars for everyone.
Everyone gets a gold star.
Participation trophies for all.
All right, well, we got about 5 minutes left, so it's time to go ahead and pack your stuff up and get ready for my closing remarks. You can follow us on Instagram and Facebook at I Slept Through Science or on Twitter at Slept Science.
If you have dumb science questions like I do, please send them to us. You can email us at isleptthroughscience@gmail.com, or you can even send us a voice memo and we'll play it on the podcast.
Please rate and review our podcast to tell other people what you think about it, subscribe to make sure you don't miss an episode, and share about our podcast on social media.
Thank you to Beth Reed Miller for the artwork. You can check out more of Beth's artwork at Beth Is Something. Okay, great. Thanks. Bye.
The bell doesn't dismiss you. I dismiss you.